What's the flaw here? What is it? P of n? What's wrong with P of n? No, this is a real assumption. In any set of n horses, depends on n, the horses are all the same color. That is a proposition. Because it depends on n, it's a predicate. It's true or it's false. Now, we know it's false, because you could get a set of a couple of horses with different color. But it is a proposition. Yeah, way back there.
So first you assume Pn for like a certain set of horses.
Yeah.
So even though it's the same number of horses, so n was the same number, it was a different set of horses. So it's not something you can assume anymore.
That's a great point. I did gloss over something here, because in the predicate, I've got in any set. So there's really a for all sets sitting out here. So I got to be careful that I establish that when I'm trying to prove Pn implies Pn plus 1. So to establish Pn plus 1 here, I assume Pn, which means in any set of n horses, they're all the same color. That I'm given. That's Pn. I've got to look at any set of n plus 1 horses. So consider any set, not a set, any set of n plus 1 horses. So you pick any set you want. Call them this, h1 through hm plus 1. Well, then the first n are a set of n horses, so I can apply Pn. Therefore, they have the same color. The last n horses in the set are a set of n horses, so I can apply Pn. So these guys all have the same color, and I'm on my merry way here. So you're right. I had to do a little bit more work, but I can do that work, and I still get a proof. Yeah? Good question. There's a problem with the base case. So my base case was here, n equals 1. In any set of one horse, the horses, let's say in the set, just to be really careful, are all the same color. No, in any set of one horses, it's only one horse, so it's the same colors itself. Yeah?
N plus 1 is the same as n. Right?
N plus 1 is not the same as n. Yeah?
So that's outside of the set. You can't have the same assumption. Because it's not a set of n horses, it's a set of n plus 1?
Well, let's see. So you're arguing I made a mistake here, right? Well, I've got horses, horse 2, 3, up to n plus 1. How many horses are in this set here?
Oh, in that set.
In this set, how many horses are there?
N.
N. So I can apply P of n to this set just the same as that set, because P of n is any set of n horses. Well, I'm picking this one now and applying Pn to it. And so therefore, they're all the same color. Yeah?
H1, H2, dot, dot, dot. Like,
Yes.
because it doesn't work if there's 2 or more, but you didn't prove it was just 1. Or one, from 1 to 2, I guess.
Exactly. Remember I told you that dot, 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 so reasonable, so easy to use, everybody uses it, was going to catch us up? The bug is in the dot, 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 and in particular it has to do with the case n equal 2. So there's 2 ways to look at the bug, dot, 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 or we didn't completely do all the inductive steps. So let's look at the case, actually it's the case n equals 1. Here, in this inductive step. Did I prove P1 implies P2? Let's just double check that worked for n equals 1. N equals 1. I've got a set of 2 horses. This becomes 2. So I've got H1, H2. There's nothing in the dot, dot, dot. It's just H1 and H2. Then this becomes H1. So sure enough, H1 is the same color as itself. This becomes, what does this become, this set of horses? What is it really? H2. All right? So I've got the color of H1 equals the color of, oh man, this is so hard to see this bug. I wrote down H2 dot, dot, dot to Hn because take out H1, what's left? What's left is H2 through Hn. But this set is only H1. What's really left here? What is this set? What is this set? H2, H1? No. You see, what is the whole set? H1 dot, 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 Hn. What is the whole thing? It's just H1. Pull out H1 and look at the rest of it. How many horses are here? 0 horses. This is the empty set. There are no horses here to compare to. Even though I got an H2, I got an HN, I got dot, dot, dot. Because generally, if n's big, this has n minus 1 horses are here. There's n total. I got n minus 1 right here. But n minus 1 is 0. There are no horses here. And so this bridge in the equality totally breaks. All right, I got color of H1 equals, there's no information here, equals the color of H2. There's no equality here. There's no horses in this set. All because of that dot, dot, dot. Do you see where the problem is by using the dot, dot, dot? For the case n equals 1, it was true for every other case of n. N equals 2, n equals 3, it's all true. All right? In fact, what we proved the base case of P1 is true. This is an argument that P2 implies P3. That is true. P3 implies P4. That is true. And so forth. We prove for all n bigger than or equal to 2, Pn implies Pn plus 1. That we proved. What is the one missing implication we did not prove? The missing link, P1 implies P2. We did not prove that. Now, is that true? No. You can find a set of two horses that are not the same color, and just because every horse is the same color as itself does not give you that. That was missing in this proof. And so we have to be really careful when you're doing these proofs that you establish the inductive step for all n bigger than or equal to the base case. And then make sure if you're going to use this really convenient dot, dot, dot notation, that you don't wind up here saying, oh, this is horses H2 through Hn, when there's no horses there, because n's 1. Any questions about this? Yeah. Great question. All right, let's fix the proof. Start with a base case of P of 2, and now I've got all this done. So therefore, that's another proof. Yeah. Say it again. This is still the same. In any set of n bigger or equal to 2 horses, all the horses in the set are the same color. That's what he's saying. And he's saying, hey, look, the proof worked here. The inductive step is just fine. P2 does imply P3. Yeah. That's right. The base case fails. All right. That's why you've always got to check the base case. Yeah.
What it does prove is that if you find any two horses and they're always going to be the same color, all horses have to be the same color.
That is correct. That's a great point. We have given a proof that if you look at any pair of horses and they're the same color, then all horses are the same color. And that's true. That is true. Of course, there are pairs of horses that aren't the same color. So the base case would fail. So always check the base case. You can prove some great stuff if you don't check the base case. All right? All right. Any other questions about that? Yeah. Yeah. Yeah, as long as it's an integer, and as long as you prove Pn implies Pn plus 1 starting there all the way out. Yeah, you can start at negative numbers if you want. Usually there's not many cases where that comes up you want to, but you can. Nothing wrong with that. Any other questions? Yeah, you can see why it was a messy homework problem. All right. So far we've seen examples of how induction is useful in proving the hypothesis is true, but not in solving the problem, per se, or even figuring out what the hypothesis should be. Now, in the last example, we're going to show you how induction can be used to prove there is a solution to a problem, and also how to find the solution. So it's actually going to be a very useful, constructive thing in this case. Now, this problem arose in the construction of the Stata Center, the building we're in now. This whole building was originally supposed to cost, completely furnished, under $100 million. That was the goal. But the first mistake they made was the first step was hiring the architect, and they hired Frank Gehry. I think MIT is now in a lawsuit with Frank Gehry. So he was the architect, and costs just went nuts. You know, as you can imagine, all these slanted walls and crazy things happening actually are expensive, and the cost quickly got over $300 million. Literally, that part's true. Now I'm going to fabricate a little bit. Now, actually, fundraising became a huge priority once they're more than $200 million over budget, and they haven't even bought the furniture yet. So some pretty radical ideas were proposed, and one of them was to build a large 2 to the n by 2 to the n courtyard and put a statue of a wealthy potential donor in the center of the courtyard. So let's draw this. So the courtyard, and of course, you know, it's computer science, so it has to be a power of 2. So it's 2 to the n by 2 to the n. And I've drawn here the case n equals 2. And we've got to get the statue of the wealthy guy in the middle. And I'm not supposed to reveal his name, so we're just going to call him Bill. All right, so Bill's got to go in the center. Now, this would be fine, except that nothing was easy with Frank Gehry. Everything is some weird thing going on. And he insisted on using L-shaped tiles for the courtyard. So the tiles that we're going to use look like this. So it's, you know, almost a 2 by 2, except you're missing that piece. So what you need to figure out how to do is tile this courtyard perfectly, leaving one spot for Bill, using tiles like this, these L-shaped tiles. And this is 2 by 2 here. So that's the task. So let's see if we can do that for n equals 2 here. Let's see, we can do a tile here. We can do a tile here, a tile here, a tile here, and a tile there. So we can. In this case, we can tile the courtyard perfectly using these L-shaped tiles, leaving one square in the center for the statue. All right, everybody understand what we're trying to do? The goal? Now I want to do it for n. So let's start proving it by induction, even though we don't know how to do it yet, because we're going to see how induction is going to help us show it's possible and maybe even show us how to do it.